The 6 centimeter diameter, 20-degree water jet strikes a plate containing a hole of 4 centimeter diameter. Part of the jet passes through the hole and part is deflected up and down. Determine the horizontal force required to hold the plate in place. So as we take a look at this, we've got our control volume drawn. We have a lot of the information there already for us. The velocity at 1 is 25 meters a second. Diameter at 1 is 6 centimeters, or 0.6 meters. Velocity at 2 is also 25 meters per second. And the diameter at 2 is 4 centimeters. Let's convert that to meters. 0.4 meters. And so I have water at 4 degrees C, at 20 degrees C, and that's going to be 998 kilograms per cubic meter. And so what are we trying to find? We're trying to find that F force here. We want to know what that is. So we're going to have to use the conservation of linear momentum. So let's make a couple of assumptions about our problem. And so as I take a look at it, I'm going to assume definitely is a fixed CV. It's not moving anywhere. Fixed CV. The way it's drawn, we have one-dimensional inlets, outlets. They're all orthogonal to the control volume. Steady flow. There's nothing in the problem that says it's unsteady. And lastly, we have, it's water, so we can say it's incompressible, or my density is constant. So we can apply all of our equations that we have. First, we'll go to the conservation of mass. Now, looking at the conservation of mass equation, I know the mass flow rate in has to equal the mass flow rate out. Now, this one's a little bit different because we don't have just a mass flow rate at 1 and 2, we also have up and down. So we really can't do much with the conservation of mass equation, but we can calculate out our volumetric flow rates. So we can look at what's coming in and what's coming out, so we can at least calculate out what the volumetric flow rate is, and then we'll be able to multiply that by density to get the mass flow rate. So Q at 1 is going to be velocity at 1, which is 25 meters per second, times the area at 1, so pi over 4, 0.06 meters squared. And so if we calculate that out at 0.1, we have a volumetric flow rate of 0.707 cubic meters per second. Same thing for Q2. Velocity at 2 is 25 meters per second. The area is pi over 4 times 0.04 because it's a smaller hole, meters squared. And so we get a volumetric flow rate of 0.314 cubic meters per second. And then the rest of the mass flow rate is leaving the control volume at these 2 points. We're not calculating that out because we really don't need it, because we're only looking at the horizontal force. So if I go and I take a look at the horizontal force, well, now we do our conservation of linear momentum equation, only in the x direction. There's our conservation of momentum. I'm sorry, I can't spell today. Momentum. There we go, that looks better. So if I look at all of my forces on the picture, air pressure is equal on both sides, pushing down, so there's no real difference in air pressure effects. We have no body forces. We're not worrying about gravity, so we're not worrying about weight and whatnot. So all we do is have a surface force, and the way that we have that force drawn is purely in the x direction, but in the negative x direction. So I have negative force of the plate. And what's that going to equal? Well, remember that's going to be the sum of all of our momentums in. So m dot v out, minus the sum of everything coming in, which is m dot v in. So we have everything coming out. So the m dot at 0.2, which is where our second diameter is, times the x component of that. We have the mass flow rate going out, we'll just call it the upper, on the upper part of it, times the x velocity in the upper plus m dot of the lower plus the x velocity in the lower. And then we subtract what's coming in, m dot 1 u1. Now, these are vector components. There is no x component for going up and down, so those are going to end up falling out. So what we're left with is the negative force of the plate is going to be equal to m dot 2 u2 minus m dot 1 u1. There are different mass flow rates because not all the mass that's coming in the x direction is leaving in the y direction, so we can't drop those down like we've done before. So if I take a look at that, you start plugging in the numbers, F of plate. What is m dot 2? Well, we're going to take our density, 998 kilograms per cubic meter. Then I'm going to multiply that by my volumetric flow rate. So what's coming out is 0.314 cubic meters per second. And then I'm going to multiply that by the velocity at 2, which is 25 meters per second. It's all in the x direction, so we don't have to angle it or anything. And then what we're going to do is we're going to subtract from that everything that's coming in, 998 kilograms per cubic meter. Then we're going to multiply it by the volumetric flow rate coming in, which is 0.707 cubic meters per second. And then we're going to multiply it by our velocity, which I'm going to drop there. So as I look at it, I've got kilogram, cubic meter. Cubic meters will cancel out. Kilogram, meter per second squared, that's going to be a Newton. That's great, that's a unit of force. So if I go and I calculate this all out, what I'm going to get is F of the plate. You plug all those numbers in, you should get negative 980 newtons. The negatives fall away, so the F of the plate, it's going to be 980 newtons to hold that plate in place. It is a positive number, and that means that we picked our direction correctly. What would happen if we got a negative number on this? Just like with the other classes, all it meant is we picked the wrong direction, and so we'd go back to our picture, flip that arrow around. So I've got 980 newtons, and it's acting to the left.